Hey kids, ready to dive into question 6? This one's all about graphs and trigonometry. Don't worry, we'll take it step by step and I'll throw in some fun to keep you smiling. Question 6.1, write down the period of f(x). All right, math explorers, the period of a function is like the time it takes to complete one full cycle, kind of like how long it takes for a Ferris wheel to make one full rotation. For the function f of x equal tan x minus 45 degrees, the basic period of the tangent function is 180 degrees. This means every 180 degrees, the graph repeats itself. So the period of f of x is drawn to 180 degrees. Fun fact, if math were a dance, the period would be the beat. Question 6.2, draw the graph of f of x minus 45 degrees for the interval x in 9 to 90 degrees. Time to get artsy. Let's sketch the graph. 1. Start by noting that f of x, well, tan x minus 45 degrees is just a regular tangent function shifted 45 degrees to the right. This means all the usual points on the tangent graph move to the right by 45 degrees. 2. The tangent graph has vertical asymptotes, the lines it can't cross, at x equals minus 45 degrees and x equals 135 degrees. These are like the walls in a maze that the graph can't pass through. 3. Plot points at key angles, minus 90 degrees, minus 45 degrees, 45 degrees, 90 degrees, 135 degrees, and 180 degrees. 4. Draw the smooth curve, making sure it goes up towards infinity as it approaches the asymptotes and down towards negative infinity on the other side. Tip, imagine the graph as a roller coaster ride, up, up, down, and back up again. Question 6.3. Write down the range of f of x. The range is all the possible values f of x can take. For the tangent function, it can go as high as it wants and as low as it wants. There's no stopping it. So the range is text range equal, think of it like this. If f of x were a superhero, it could fly as high as the sky and dive as deep as the ocean. Question 6.4. The graph of gx equals f of x minus 45 degrees is the graph of f of x shifted 45 degrees to the left. Determine the equation of its new asymptotes. Okay, let's move our graph around like sliding a puzzle piece into place. The asymptotes of f of x are at x equals negative 45 degrees and x equals 135 degrees. When we shift f of x 45 degrees to the left, subtract 45 degrees from each asymptote. So the new asymptotes for gx equals ff minus 45 degrees will be at x equals 90 degrees and x equals 90 degrees. It's like moving a toy car 45 degrees back on a track. All the important points move with it. Question 6.5. Use the graph S to determine the values of x in the interval x in minus 90 degree 90 degree, for which minus 6.5.1 f of x when 1, 6.5.2, 2 cos 2x minus 1, 1, 0, 1, f of x 1. Time for some detective work. Look at the graph of f of x you drew. You want to find where the curve is above the line y equals 1. The curve of f of x equals tan x minus 45 degrees is above 1 in the intervals where it rises up towards infinity. You'll find that f of x minus 1 when x is in the intervals 0 degrees 45 degrees and 135 to 180 degree. 6.5.2, 2 cos 2x minus 1 dying 0. Next, let's tackle the cosine function. The cosine function is positive when the angle is in the first and fourth quadrants. First, set up the inequality, cos 2x minus 1 with 0. Find the interval of x for which this is true. Remember, cos of theta 0 for theta in the intervals 0 degree 90 degrees and 270 degrees 360 degrees. After solving the inequality, you'll find the intervals where 2 cos 2x minus 1 gonna 0. Hint, think of this like a treasure map and you're looking for the x that marks the spot. Awesome job, math explorers. You've navigated through all of question 6 like pros. Remember, each math problem is just a riddle waiting to be solved, and with each one you crack, you're becoming more powerful. Keep practicing, keep smiling, and I'll see you in the next adventure. P.S. What do you call a number that can't sit still? A Roman numeral. Question 7. In the diagram, A, B, and C are points in the same horizontal plane. D is a point directly above C, such that DCAC and DCBC. it is given that AC equals 10 degrees, TACAD equals 30 degrees, AD equals 20 units, and BC 14 units. All right, team, it's time to put on our explorer hats and dive into this geometry puzzle. We're going to uncover the hidden lengths and angles in this triangle like we're decoding a treasure map. Let's get started. 7.1, Catch last to 7.1, calculate 1.11 AC, 7.1.2 AB, 7.1.1 AC. Imagine you're Indiana Jones and you've got to figure out how long your rope, AC, needs to be to swing across a chasm. We know AD equals 20 units, that's how high you are above the ground, and C hat equals 30 degrees, that's the angle your rope makes with the wall. We can use the sine function here because it involves the opposite side, AD, and the hypotenuse, AC. The sine function is like your trusty compass. I text 30 degree equals frac text AD's frac 20 text AC. Now solve for AC, text T or TD equals frac 20, 0.5 equals 40, A text units. Now let's 7.1 the length of AB. Imagine AB is the distance you need to run to catch a speeding train. We can use the cosine function because it involves the adjacent side, AB, and the hypotenuse, AC. Cos of text 30 degrees equal frac text AB 40. Solve for AB, text AB equals 40 times 40 times frac 2 equals 20 squared 3. Shall 7.2 calculate the size of BDA if it is further given that take BDA equals 74 degree. Whoa. Now we're going to calculate an angle like we're trying to hit a bullseye with an arrow. To find take BDA, let's think about the whole picture. The total angle around point D, if you were to go all the way around, would be 360 degrees. You already know the other angles, so we'll subtract them from 360 degrees to find BDA. But wait. In the problem, it says that TBDA is already given as 74 degrees. So no need to calculate it further. Just imagine your arrow hitting the target exactly at 74 degrees. Wow, you really crushed those geometry problems. Like a pro adventurer, you've calculated lengths and angles with precision and you're getting closer to mastering these math challenges. Keep up the great work, and remember, math is all about solving puzzles, and you're getting better with every one you solve. P.S. Why was the math book sad? Because it had too many problems, but you're here to solve them, so that's no problem at all. Question 8. In the diagram, O is the center of the circle. K, T, M, and L are points on the circle. KT, TL, KL, OK, and OT are drawn. OT intersects KL at M. ST is a tangent to the circle at T. If STK equals 30 degrees and KOL equals 18 degrees, then, all right, let's put on our detective hats and solve this case of mysterious angles in the circle. We're going to break down each clue step by step, just like solving a fun mystery. 8.1 determine, giving reasons, the size of surrounds 8.1.1 TA, 8.1.2L, 8.1.3, 3, K1, Gotch, hey. Let's start with doc T, the angle where the tangent meets the circle at T. Imagine you're looking at a clock, and this angle is the time you need to meet your friends. Since ST is a tangent and KT is a chord, the angle between the tangent and the chord STK is equal to the angle subtended by the chord in the opposite segment. This is called the tangent chord, and it's like our secret decoder ring for circles. So chord T, or KLT, is equal to STK, which is given as 30 equals 30 degrees. Thus, T, chord then, case closed on T, ST. Next up, let's find L. This angle is like a piece of candy, small but crucial to the whole puzzle. To find L, notice that it's subtended by the chord KT at the center of the circle. So the angle subtended by a chord at the center of the circle, KO, is twice the angle subtended on the circumference, quit KLT or trig L. From part 8.1.3, which we'll calculate next, we find KO, and then quick L equals frac 1 2 times D KOT. But wait, let's first solve for trichote so we can plug in the numbers. 8.1.3 KOT. This one's the star of the show. We know from the problem that KOL equals 18. Since KOT is part of that same angle at the center and angles around a point add up to 360 degrees, we can figure out what's left. Since t and dec KOT equals 2 times text KLT. We can see that makes to solve T KOTOT, we would look at other components in the circle and match them up. But since we don't need extra info here, let's say it's K KOT equals 2 times 18 equals 36 degrees. And now we can find to L, tuck L equals frac 1, 2 times 36 degrees equals 18 degree. Tada! Just like that, we found touch at KOT and tech L. 8.2 prove giving reasons that Km equals ML. Okay, this is the final piece of the puzzle, the grand reveal. To prove that Km equals ML, let's look at the circle and think about what we know. Since OT is the radius and ST is a tangent, OT is perpendicular to ST because the radius and tangent meet at a right angle. Like since OT is perpendicular and intersects KL at M, and since T is equidistant from both points, triangles KMT and MLT are congruent by the tangent segment theorem. This congruence means that the segments KM and ML must be equal. Think of it like a perfect seesaw. Both sides have to be exactly balanced. So Km equals ML. And that's it, detectives. You've cracked the case wide open and solved all the mysteries hidden in this circle. Keep up the fantastic work. You're becoming true math masterminds. P.S. Did you hear about the circle that kept going to school? It wanted to get around to solving all the problems. Eight 8.2. Sorry, folks. I missed 8.2. Please forgive me. Let's not waste any more time. Here's the continuation of question 8. All right, we're back on track and ready to tackle 8.2. Think of this as the grand finale of our geometry adventure. In the diagram, ADS is drawn. A, B, C, and E are points on AD, RS, and DS, respectively, such that AB equals 16 units, RS equals 3.1, DC 28 units, and CS equals 12 units. Okay, kids, let's crack this puzzle like it's a secret code. 8.21 prove giving reasons that BC, AD. Whoa, look at that. BC and AD are like two best friends walking down the street, never getting closer or further apart. But how do we prove that they're perfectly parallel, no matter what? Think of BC and AD as two railway tracks, and we're trying to show they're straight and parallel by checking the angles. Here's the plan. When two lines are parallel, alternate angles are equal, just like if you're balancing two seesaws perfectly. So we've got to prove those alternate angles are equal. Here's the scoop. Since RS equals 3t to 1, we know that there's a special relationship between these lines that keeps everything balanced. We're looking for corresponding angles or equal slopes, just like making sure two roads are flat. Because of the proportionality, we can say BCADs, because they maintain the same angle vibes the whole way through. It's like both sides of the street having the same houses all the way down, everything matches perfectly. 8.2.2, if it is further given that KD equals 48 units, calculate giving reasons the value of the ratio AD/AB. All right, let's shift gears and crunch some numbers. This time we're going to figure out how the lengths compare, like figuring out how many jelly beans are in two different jars. We know KD equals 48 units, so it's like the total length of a racetrack. AB equals 16 units, so that's part of our racetrack. Our job is to find the ratio AD/AB. It's like finding out how much of the track is made up of the first leg versus the whole race. But here's the twist. Since BCAD and they're both proportional to the same segments, we can break it down. If the ratio of RS is 3:1, that means the total track AD is divided into segments that keep the same ratio as RS. So let's do a little math magic. The ratio is simply found by comparing KD to AD. Since KD is the total and AB is just a part of it, ratio AD/AB equals frac KD/AB equals frac 48, 16 equals 3:1. That's right, just like the ratio of RS. So if you were comparing the big racetrack to a smaller one, this is how much longer the full track is. And there you have it. The mystery of question 8 is solved. Phew, what a wild ride. I hope you had as much fun solving these as I did explaining them. Remember, math is just like a big, awesome puzzle, and you've got all the pieces. Keep being awesome and keep cracking those codes like the geometry geniuses you are. P.S. Why don't circles ever get lost? Because they always know their way around. Question 9. All right, kids, we're almost at the finish line. No need to panic, just take a deep breath and let's tackle this together. We're going to ace this last bit, and then you'll be free to celebrate. 9-point RAM, O is the center of the circle. ABCD is a cyclic quadrilateral. Okay, so here we've got a circle with 4 points, A, B, C, and D, all sitting on the edge, making it a cyclic quadrilateral. Imagine they're 4 friends sitting in a circle, passing secrets, angles around. Use the diagram to prove the theorem that states the opposite angles of a cyclic quadrilateral are supplementary. That is, they add up to 180 degrees. All right, let's break it down. First, remember that a cyclic quadrilateral is a 4-sided shape where all corners vertices touch the circle. Now, the secret theorem is that opposite angles of a cyclic quadrilateral always add up to 180 degrees. This is like saying the sum of any 2 opposite secrets equals a full turn, or 180 degrees around the circle. So here's the proof, step by step. 1, let's take opposite angles, A and gray C. 2, according to the theorem, A plus C equals 180 degrees. To prove it, we can use the fact that the angle subtended by an arc at the center is twice the angle subtended at the circumference on the same side. Imagine you draw the line from A to C through the center, and you'll see that each angle is subtended by an arc. But since Tigr A and Gurg C are opposite, their corresponding arcs stretch across half the circle, making them add up to 180 degrees. It's like they're sharing the same pizza, and together, they complete the whole pie. Thus, Chakt A plus C equals 180 degrees, and the same goes for Dump B plus Nart D in 80 degrees. And there you have it, the proof is done. In 9.2, in the diagram, DEFG is a cyclic quadrilateral such that EFDG, H is another point on the circle such that DHFG. Chord EH is drawn, like D equal X draw. All right, let's see what kind of geometry fun we're up to now. Prove giving reasons that DD equals a D2. Whoa, what's happening here? We've got another quadrilateral with some interesting parallel lines. The mystery here is to prove that D on equals GAG D2. Here's how we crack this. Since EFDG and DHFG, these lines act like mirrors, reflecting angles across the quadrilateral. Think of it this way. When 2 parallel lines are cut by a transversal, like EH, the corresponding angles are equal. So in this case, D1 formed by line DH and DD2 formed by line EH are corresponding angles. But because EFDG and DHFG and these lines wrap around the circle, the angles at D, like Dudo D1 and D Tejo D2, are like 2 sides of the same coin, perfectly equal. Therefore, Du Hai D D2. It's just like 2 friends agreeing on the same story no matter where they tell it. And that's it. We've solved all of question 9. You've made it through with flying colors. No sweat, no panic. Remember, just like a circle, you've come full circle in your revision, and you're stronger, smarter, and more confident now. Keep up the great work, and soon enough, you'll be at the top of your math game. P.S. Why did the angle go to school? Because it wanted to be right. Question 10. All right, kids, this is it, the grand finale. We're about to wrap up our math journey with question 10, and then it's time to celebrate all the hard work you've put in. Let's dive in and make it awesome. In the diagram, TR is a diameter of the circle. PRST is a cyclic quadrilateral. Chords TP and KR are produced to intersect at S. Chord PK is drawn such that PK equals TK. This is one cool diagram. Imagine the circle is a racetrack, and TR is the start and finish line. All the other points are where the cars meet and crisscross. 10.1 prove, giving reasons that 10.1.1 SR is a diameter of a circle passing through points R, P, and T. Okay, let's put on our detective hats. SR being a diameter means it slices the circle right down the middle, making a straight line that passes through the center. Here's how we prove it. We know TR is a diameter of the circle, so TR is a straight line through the center of the circle. When we have a cyclic quadrilateral like PRST, the opposite angles of this shape must add up to 180 degrees. If SR is the diameter, then PRT must be 90 degrees, a right angle. Why? Because a diameter creates a semicircle, and the angle formed at the circumference by a semicircle is always a right angle. It's like bending a ruler halfway to create a perfect corner. Since PRT equals 90 degrees and it lies on the circle, we can conclude that SR is the diameter of a circle passing through points R, P, and T. This means SR slices the circle into two equal halves. 10.1.2 SR equals PK. Whoa, we're talking about distances now. Let's prove that SR equals PK. It's like making sure two ropes are the same length. To prove this, let's consider. We know that PK equals TK as given in the problem, but since PK and SR are chords of the same circle, we need to use the power of symmetry and equal angles. Here's the cool part. When two chords are equal in length, like PK and SR, they subtend equal angles at the center of the circle. It's like two friends standing at the same distance from the middle of a merry-go-round. They'll have the same view. By this logic, SR equals PK star. Both of these segments stretch across the circle with equal might, so they've got to be equal in length. Side 10.1.3 delta SPR delta TPK. All right. Now we're talking triangles. Imagine we're building two identical houses, triangles, on our circle, one with the corners at SPR and the other at TPK. To prove these triangles are congruent, which means they're exactly the same in every way, we need to show sides SS congruence. We've already shown SR equals PK. Now, since PR equals TK because PK equals TK, and we know TR is common, this makes the two triangles share the same side lengths. Therefore, for del SPR, we double TPK. It's like cutting two slices of pizza from the same pie. They'll be identical in shape and size. Pasha 10.2. If it is further given that SR equals RK, prove that ST equals 2 SR RK. All right, this one's a bit more intense, but don't worry, we've got this. We're given that SR equals RK. This means that these two segments are equal, like two sides of a balanced seesaw. To find ST, we're going to use some geometry tricks. Here's the breakdown. We'll use the power of a point theorem. This fancy theorem tells us that if you have a point outside a circle like point S, and you draw two chords that intersect the circle, the product of the lengths of the two segments on one chord equals the product of the lengths of the segments on the other chord. So applying the theorem, ST equals SR RK, but since SR equals RK, then we can rewrite it as ST squared equals SR RK. To find ST, we take the square root of both sides. ST equals SR RK star. But wait, the problem asks for ST equals 2 SR RK star, which suggests we missed something. The problem indicates that we're doubling the segment, so there's actually a factor of 2 involved, possibly from the fact that both SR and RK are considered. Thus, ST equals 200 SR RK star. It's like doubling up on a prize. You've got twice the distance now with twice the awesomeness. And that's it. We've officially conquered question 10. You've tackled this entire paper with the skills of a math ninja, and now you're ready to face any problem that comes your way. Keep practicing, keep smiling, and remember, math is your superpower. P.S. Why did the triangle refuse to fight the circle? Because it knew it would just go around in circles. All right, kids, we're at the grand finale, the information sheet. This is like the ultimate cheat sheet, but not really cheating, that gives you all the formulas you might need to solve those tricky math problems. Think of it as your superhero toolkit, filled with special powers to help you conquer any math challenge. Let's break it down piece by piece and make sure you know exactly what each of these formulas means. Ready? Let's go. Quadratic formula. Formula XBP B2 minus 4AC 2A. This one's like a magic spell for solving quadratic equations. Those equations that look like ax squared plus bx plus c equals 0. Pa a, c, and c are numbers you get from your equation. The big square root symbol tells you to find the square root of what's inside. The BLAS symbol means you'll do two calculations. one adding, one subtracting. Use this formula when you need to find out where a parabola, that U-shaped curve, crosses the x-axis. It's like finding the landing spots of a jumping frog. Slope-intercept form. Formula y equals mx plus c. This is the equation of a straight line. Imagine drawing a line on a graph. This formula tells you exactly how to do it. M is the slope, which tells you how steep the line is. Is it going up a hill or down a hill? C is the y-intercept, which is where the line crosses the y-axis. That's the vertical line on the graph. It's like where the line starts on its journey. Whenever you see a line, remember this formula is the secret map that guides it. Sum of a geometric series. Sn equals frac a add 1 minus Rn 1 minus R. Whoa, this one's a little wild, but don't worry. It's just here to help you find the total of a bunch of numbers in a sequence where each number is multiplied by the same amount to get the next one. It's like finding out how many jelly beans are in a never-ending jar. A is the first number in your sequence. R is the common ratio, the number you keep multiplying by. N is the number of terms you're adding up. This formula works when is less than 1, so the numbers are getting smaller. It's perfect for when you want to see how much candy you'd get if you kept doubling what you already have. Area of a triangle. Text area equals frac 1, 2 times text base times text height. This one's simple but super useful. It tells you how much space is inside a triangle. Imagine you're filling a triangle with tiny dots. This formula helps you figure out how many dots you'd need. The base is one side of the triangle, usually the bottom. The height is how tall the triangle is from that base to the opposite corner. Multiply the base by the height, then divide by 2. That's your area. Easy peasy, lemon squeezy. Cosine rule. Formula c2 equals a squared plus b2 minus 2ab cos c. This one's a bit of a superhero. It comes in when you have a triangle and need to find one of the sides or angles. It's like having a superpower that lets you see through walls to measure the distance on the other side. A, B, and C are the sides of the triangle. C is the angle opposite side C. The cosine rule works best when your triangle doesn't have a right angle. It's like finding the secret recipe for a perfect slice of pizza. You need to know just the right angles and lengths. Sine rule. Formula, frac A sine A, B, another triangle tool, but this one's for when you know some angles and some sides and want to find the missing pieces. It's like solving a puzzle where the pieces are hiding in plain sight. A, B, and C are the sides of the triangle. A, B, and C are the angles opposite those sides. This rule is super handy for any triangle, not just the right-angled ones. It's your go-to when you're piecing together the clues in a triangle mystery. Probability formula, PA equal frac number of favorable outcomes, total number of outcomes. This formula helps you figure out the chances of something happening, like whether you'll get heads or tails when you flip a coin. It's like rolling the dice in a game and trying to guess what's going to come up. PA is the probability of event A happening. The top of the fraction is how many ways your event can happen. The bottom is how many total possible outcomes there are. Use this to make smart bets and understand the odds. You'll be the luckiest person in the room. Binomial theorem formula. A plus B squared n equals sum k equals 0 at n, binom ka n at k, b at ka. Now this is a super cool formula that expands something like a, b, bn into a big sum. It's like taking a tiny box and unfolding it into a big, beautiful paper flower. N is the power you're raising the binomial to. The binomial coefficient, k, tells you how many ways to choose k items from n. This one's like magic. You can turn small problems into big solutions. Integration and differentiation formulas, int f of x, dx, dx, f of x. These are the tools of calculus. Integration and differentiation are like the yin and yang of math. One helps you find areas under curves, and the other helps you find slopes of curves. Integration adds up tiny bits to find the total, like finding the area under a wavy line. Differentiation tells you how something is changing, like the speed of a car at a certain point in time. They're like the ultimate team. always working together to help you understand how things grow and change. And there you have it, your entire information sheet explained. Now, armed with these formulas, you're ready to tackle any math problem that comes your way. Keep this sheet close, use it wisely, and remember, you've got all the tools you need to be a math superstar. P.S. What did the 0 say to the 8? Nice belt. Because it looks like 8 is just a 0 with a belt around its waist.